Okay, so I think we can get started. Welcome everybody to this session of GSI 17. So this session is organized by myself. My name is Antonio Mucherino from University of Rennes 1 and Douglas Gonçalves from the Federal University of Santa Catarina in Brazil. So you would excuse him if he's not here today. His flight was a little long and expensive. So I will represent both of us. So I prepared just a few slides, 2 minutes to introduce the session. So we have 6 papers that are going to be presented. The first one is will be given by, it's a presentation given by myself. It's a joint work with Douglas Gonçalves. So I say this now, I will not repeat it again later. And then other 5 presentations. Good point to keep in mind is that we have 2 hours, so this makes 20 minutes per presentation, including the discussion, the questions, and so on. So we should try to keep the time. So this is a message for speakers. And for those of you who attended the opening, it was recalled, the death of Michel Desat was recalled during the opening. And so I take the chance to remind you all that in collaboration with another colleague, Carlier Lavor from Brazil, we are collecting papers in this moment for a special issue of optimization letters. The title of the special issue will be the same of this special session. And so this special issue was already planned at the time we learned about the death of Michel Desat. And so finally we decided to devote the special issue to his memory. So the deadline for submission is in 2 months, at the end of this year. But in case you are interested in submit a contribution, you can just drop me an email. I can see if I can negotiate a little extension with the editor-in-chief. This is already the second deadline, so we cannot extend for so long, but we can still discuss about this. So, okay, I put here a last slide, a picture that we took, Carlier Lavor and myself in Varna in 2012 for a conference that Michel Desat and Michel Petitjean organized in Bulgaria in 2012. Okay, so that was just the introduction. Where is the how can I close my presentation? It doesn't work with escape. And now we need to open this one. And at the end of the presentation, I will need to run the video. It's just at the very end. Okay, thanks. Okay, so I will start now with my own presentation, co-authored with Douglas Gonçalves, and that will be on a dynamical distance geometry approach. In order to introduce the problem, I will first of all recall the definition of static distance geometry problem. I consider a simple weighted undirected graph G, where the edge set represents a given set of objects. I say object in general because the entity of the object depends on the application at hand. Then E is the vertex set, the edge set. And there is an edge in this case, in this graph, where I know a distance information about the 2 connected vertices, 2 connected objects, and the weight that is associated to the edge gives a numerical value for the distance between the 2 objects. So the distance geometry problem in dimension K is the problem of finding a realization X such that for all edges in the edge set of my graph, this constraint is satisfied, which means that the distances between realized vertices correspond to the distance that is the weight delta of in my graph G. Here I use this generic symbol because there can be different situations. I can have an inequality here when the distances are exact. Exact distance is a distance that I can fully trust, or a distance that I want to be satisfied in full. Other cases I can substitute this symbol with an inclusion operator when I have an interval. I want that my real distance is contained in a given interval. In this case, my distance has a possibility to move in a certain range. In other cases, I have approximated distances. So I have an idea of how the distance will be, but I'm not sure about how I can rely this on this numerical value that I have. And so when I have an instance of this kind, I'm sure that I will not be able to realize, to satisfy all the distances that I have in my graph G, but an error on every distance needs to be introduced when I obtain the realization. And the idea in this case is to identify the realization that is able to minimize as much as possible the error, the overall error that is introduced in the distances. This is a very famous paper dated 1979 that proves that the distance geometry problem is an NP-hard problem, strongly NP-hard. There are several methods that have been proposed since then for the distance geometry problem. This is a non-exhaustive list. And I add now for this presentation another method that I will consider today in my presentation. It's this, as all of you knows, this is a general method for global optimization, for local optimization actually. But it can be very useful also in some cases for distance geometry when the starting point that we can give to a gradient descent method is quite close to the solution that we are looking for. Then I will explain more on this point in the next slides. So when we have a method for when we transform, when we reformulate our distance geometry problem as an optimization problem, we need a penalty function, like for instance this function sigma, where the satisfaction, the violation of the constraints is measured by the genetic term of this function. And here I also included a value pi that represents the importance of the distance, because in the case in which the distances that I have are approximated, so I know that I will not be able to satisfy all the distances, I may have some idea on which distances are more important than others. You will see this in the application that I will show you in a while. And in this case, I can give higher priorities to important distances, lower priorities to distances which I care a little less. Important thing about this function is that it's differentiable for every point, such that pi multiplied by the value of the distance is strictly greater than 0. Yes? It's a function of x. Yeah, you're right. I think I missed something. Yeah, I think I missed something there. Yeah, I will check this. I'll tell you later. So a few words about the non-monotone spectral gradient method that we consider in this later. I will consider later in this presentation. So as I mentioned, it works well for local optimization. If my function is strictly convex, it's able to give me the solution to the problem, but it's not always the case, of course. The way we compute a step on the opposite direction of the gradient is done in a way that I cannot explain details for lack of time, but I can tell you that then it makes the convergence properties of the algorithm depend on the spectrum of the Hessian, and that's why we call this algorithm a spectral gradient descent method. And since our function is not convex, but it's a more general function, we use this initial step for the opposite direction of the gradient just as an initial guess, and then we improve it by performing a non-monotone line search. And so this is the algorithm that we will consider now to solve some instances of the dynamical distance geometry problem. Okay, so the idea here is to introduce the dynamics in distant geometry problems. So I have, as in the previous definition, I have a simple weighted undirected graph. The vertex set is a little different now because it's a set product of two sets, a set V that contains a set of objects, just like in the previous definition. But then I also have T. T represents the time. Time here is represented with a set. You can imagine that T is the set of the first n integer numbers. So it's a discrete representation of the time, like frame 1, frame 2, and so on. So the vertex of the graph is actually a pair object U and time Q, or vertex V and time T. And pairs of pairs are in the edge set, and I have an edge between these two vertices if I know the distance, a distance information about the two objects at the two different times, T and Q. And my weight function is here a little more complex because in these applications it's important that I couple the distance information with the importance of the distance. And so I have delta, like before, but also have pi, so the importance of the distance. And the problem, we can say that the dynamical distant geometry in dimension k is the problem to identify the realization x such that my function sigma is minimized. Now, I start with the applications. I start with a very simple example. Imagine you have particles in a 2D box that move, and I can represent this motion, this animation, by distances. In general, we represent these motions by trajectories of the objects in the space. But from this, the trajectories are able to give us the positions of the object, of the particle at every instant of the animation. And from this information, I can compute distances. I represent everything by distances. Once I have this, I can introduce new distance constraints. So the advantage in doing this operation is that once I have the representation by distances, I can more easily modify some constraints or introduce new distance-based constraints. So I start with a simple animation where I have some particles on the perimeter of this 2D box, and there is a central point, and the idea is to, the animation consists in moving these points. This animation goes 10 by 10 frames, and these points tend to reach the center at frame 100. So it's I called it the black hole instance because all the points tend to reach the central point. Now, I want to manipulate this animation. I want to keep the main features of the animations, but I want to add some distance constraints. So, in order to preserve information about the original animation, I use here this kind of distances from every vertex V at frame T to the same vertex at the previous 3 frames, so at frame T minus 1, minus 2, and minus 3. These distances are able to represent the motion. If I would solve this dynamical distant geometry problem only with this information, this distance information, I would reconstruct exactly the same animation, modulo translations, rotations, and reflections. But I would obtain more or less the same. But our interest here is to manipulate now this animation. So what I impose here with the second set of constraints, is that I want that the distances between the central point and all the other points is always greater than a certain delta. So this goes against the original animation. During the original animation, all the particles reach the central point. Now I want them to have the same kind of animation, but they should not reach the central point. So you see, this distance, this instance of the problem is not feasible if I suppose that the distances are exact. I cannot satisfy at the same time this set of distances and this set of distances. That's why the idea to introduce priorities is important here, because this is what I want. So this set of constraints has high priority. Instead, the original animation has a lower priority. So as far as they can both be satisfied, it's fine. But if they are in contrast, I will prefer this rather than the original. And so, if I solve this instance of the dynamical distance geometry with the spectral gradient algorithm, where the starting point is the original animation, so something that's quite close to what I'm looking for, I obtain an animation that looks like this. You see here at frame 60, and the animation starts to change because the particles cannot go too close to the central point, but still you can see that there is something left from the original animation. And you see now the particles tend to go closer to reach a black hole, but the black hole is not anymore one, there are two, okay? But most importantly, it's not C anymore, the attraction point. Other two attraction points were identified in the animation. Okay, so now this was a toy problem. But now, why we do this? Why we are studying this kind of dynamical distance geometry problems? I have here another in application. I didn't check my time. I hope that I think I have still a few minutes. And so here, this is in the context of human motions, retargeting of human motions. The idea is to start from the animation of a human character, here represented by a skeletal structure that resembles the human body. And the idea is to, starting from an animation that is already known, and a known animation can be obtained by motion capture, very quickly. There are captors that can be placed on human body. With infrared camera, you can obtain the positions of these sensors at every frame of a motion, and then you can construct the animation on a skeleton. And this is quite easy to do. With the new novel technologies, the problem is when you want to animate a different character, like for example, I have an actor that makes a scene that in a cartoon should be played after by a monkey, and the morphology of this actor is evidently different from the morphology of the monkey. And so how to make a monkey, a skeleton of a monkey, behave like the actor. And so this is the main point. So I have the same kind of problem that I showed you before, but here the particles are the joints of a skeleton. And the particular thing is that distances between some pairs of joints are fixed because they represent the bones. And so the distances, part of the distances represent the skeleton, the skeletal structure that is represents the character. And the other distances represent the movement. For instance, distance between this joint and this joint represents the movement of the leg. In the basic approach for making this kind of retargeting is to transfer the angles between the bones. But this approach is not the best one, because it doesn't allow to avoid collisions of joints. For instance, if I have my head here, and now I want to retarget this position, this posture, to a guy that has longer arms, evidently my hand goes in the brain. So it's something that you would not like to have. And so that's why we believe that with a distance-based approach, we could have good results by avoiding this kind of issues. So we developed a method that I have no time to discuss now that is able to, once you modify the bones of the character, you also need to modify accordingly the distance it represents the motion, because imagine these legs become shorter. This distance here should not be the same, should be proportional to this original distance. So there is a technique we developed to obtain a set of approximated distances, and from this set of distances can be used to represent an instance of the dynamical distance geometry problem that here we can solve always with the non-monotone spectral gradient, but frame by frame, because every frame represents a posture of the guy of the character in the animation. And if we do this, if you can please run my video. I have just other 2 minutes, a little video showing some preliminary results. It's this one, yes. So this is a paper that is being presented right now in Barcelona in a conference named The Motion in Graphs, The Motion in Games, sorry. And I need to stop it and discuss. And okay, here we have the original character, the original motion, the same with the same motion on a skeleton that has a forearm that is 30% shorter. And this is done with angle transfer, and this is our method. You can see that when you have the angle transfer method, the joints, hips and hand tend to collapse. And this should be not the case. Instead, in our result, we see that the posture is a little different. If you look closer, you see that it changed a little, but it allowed to avoid the collision. And I have another example, then I will stop. I will not run the video until the end. Here, the upper arm is 30% longer. So you have the animation, and you see this is the original. Here, the arm is longer, yeah? And so you see that there is a collision here with the knee, and here we have a distance that is satisfied. The posture is a little different, but it avoids to have this kind of collisions. Okay, I have other examples, including some limitations of the approach that I think I already talked too long. So I will stop here, and maybe if there is one question I can accept, and then we can step to the next speaker. Yes. This is a very nice question. Actually, we don't have this kind of constraints now, but they can be included later. It's true that, yeah, okay, yes, but the information about the angles can be represented by distance constraints. But yeah, this is one of the future works. And right now, we consider only distance. We know that this is a human body. It tries to simulate a human body, but the guy could. I can show you the rest of the video in the meantime, because at a certain point, since we work only with distances here, when I do this, my body goes on a plane, and so to have this or to have this becomes the same, and it's going to be in this example. And so when we will include, it's going to happen here. At a certain point, it goes on the plane, so we have a symmetry, and the arms go on the other side. And this, when we include this kind of constraints, this will not happen anymore. But right now, we only have distances obtained from the original motion. Okay, I think that it's enough. Thank you. Okay.